Welcome back. We're going to be looking at Hooke's law today and how to use it, and then a simple description of how to calculate K, and then what forces can be calculated from Hooke's law. But let's first just take a look at what it will be describing. Here we have a spring and then a weight hanging on it. It's not moving, and that's why it is a little yellow line here. That will be its equilibrium point. If we set it into motion, it would oscillate up and then down and up and down, up and down. Our particular circumstance is idealized, meaning we don't take into account any losses of energy, like through friction or pushing air out of the way or noise, anything like that. In our idealized version, this will just oscillate up and down forever. Okay, and we're going to be looking at how Hooke's law can help us in a few situations. In order to do that, we need to look at a few force vectors here. We have this green one. That is the force that the spring uses and tries to pull the weight up while gravity is trying to pull it down. And at equilibrium, while it's standing still right here, it's not moving, and therefore the green and the red are equal. However, sometimes things move, and when that happens, if it's on its oscillation upwards, then you can see here that the spring isn't pulling as hard the closer it gets to its maximum height. And yet the red here, the gravity, is still pulling just as hard. Okay, let's take a look back to equilibrium again, and then as it goes down, and not quite to the bottom, but still on its way down, you can see that here, this has grown. It has gotten a lot larger. And that'll continue until you get to the maximum low level there. Although gravity doesn't change at all. That force is going to be constant. Okay, back to equilibrium. Now, here is Hooke's law, and it says that the force is proportional to those two things multiplied together. That is the change in the length of the spring. So you're pulling on the spring, and the spring's pulling back. This, the K value there, the spring constant, that is unique to each spring. And as you pull the spring constant will tell you how much it's going to be pulling back for every, say, centimeter that you are pulling it, or any measure of length. So the harder you pull, or the longer you're pulling it, the more the spring is pulling back. All right, let's use this in a problem and see if we can calculate what K is first. That's what that is there. And then after that, we'll use Hooke's law to find out what force is necessary to pull that same spring 7.8 centimeters. Okay, so here's our situation. We have a spring with nothing on it, and it's just hanging there. That's where the yellow line is. Then we put a 100-gram weight on it, and that causes it to be extended 3.4 centimeters. Now from that, we're going to want to try to find our K for the spring. So we need Hooke's law. So there it is. And what do we know? We know the mass, and we know the displacement. We know that it was 3.4 centimeters. So let's color code these so we know what's what. The force is going to be the K of the spring that we don't know times the 0.034 meters. That's why we have these here. There's the distance. This is the thing we're looking for, and that's what we know. And we know this from Newton. F equals ma, okay? We know the mass, and on Earth it is g, that is the acceleration. So let's plug these in, rearrange it. It becomes a very simple little algebra problem because this was a linear relationship. And when we clean it up, we get 28.9 newtons for every meter that you pull that spring. So, although I wouldn't recommend pulling most springs a meter, you're going to find that the K is operational within perhaps a few centimeters at most, and if you pull it more than that, the spring will deform and you'll damage it, and then you'll end up with a different K. So in labs, be careful with the springs that you're using. It's not always a meter you could pull them. All right, now we have our K, and we'll try to calculate the force needed based on Hooke's law and our new K, to make the spring go down to 7.8 centimeters. So there's Hooke's law. We know our K, and it's a simple linear thing. You just plug everything in and you'll get the force necessary. Since we need that right there, that's how far we're going to do it. We have to change it to meters, of course. And then our K is right there. So you just multiply them together and you get 2.3 newtons. So it's not that bad. All right, next time we'll be looking at some deeper versions of harmonic oscillations and how Hooke's law is used to help derive some of those. All right, see you next time.